permutation is a 1-1 function from a set onto itself. Now, so far in this course, we've used a special notation for permutations, and here's an example. This is a permutation on the set 1, 2, 3, 4, 5. And we think of the permutation as acting vertically downwards. So 1 goes to 3, 2 goes to 4, 3 goes to 5, and so on. Now, we've written out this permutation in function form using arrows, and here it is. And what we want to do is we want to develop an even shorter way of representing permutations. And to see that, let's work through this permutation and try and see just what's going on. Well, first of all, 1 maps to 3, so let's put that down here. 1 maps to 3. And what happens to 3? Well, under the permutation, 3 goes to 5. So let's put that down. 3 goes to 5. Next, 5 goes to 2. So bring that down. 5 goes to 2. Then 2 goes to 4. Putting that down. And finally, what happens to 4? Well, 4 maps to 1 under permutation. And you notice that what we've done is we've completed a cycle. And this cycle contains all the information about the permutation because it tells us exactly what the permutation does to each element. Well, keeping the cycle in mind, we can now write down our permutation in a simple way, like this. What we've done is we've written down the elements, but in the order in which they appear inside the cycle. And the way we read the permutation in this form is 1 goes to 3, 3 goes to 5, 5 goes to 2, 2 goes to 4, and when we get to the end here, the permutation takes 4 back to 1. Well, we call this the cycle form of the permutation. In this case, we started with 1, but you see, we've got a cycle. We could equally well start at any element, and provided we write down the elements in the order in which they appear in the cycle, we'll get the same permutation. Well, in this program, we're going to use the cycle form of permutations to study permutation groups. In this case, we've got a cycle of length 5. We call it a 5 cycle. But in general, the cycle structure of a permutation won't be as simple as this. If we look at this permutation, for instance, using the same representation as before, 1 goes to 2, 2 goes to 5, and 5 goes to 1. So the permutation cyclically interchanges 1, 2, and 5 in that order. But that doesn't cover the whole effect of the permutation, because we still have 3 going to 4, and 4 going to 3. So the permutation has a second cycle as well, the 2 cycle 3, 4. And the whole permutation is a combination of a 3 cycle 1, 2, 5 and a 2 cycle 3, 4. This permutation of 5 symbols has a different structure. 1 goes to 2, 2 goes to 3, 3 goes to 5, and 5 goes to 1. So it contains a 4 cycle 1, 2, 3, 5. But there's still the 4 to be accounted for. The permutation takes 4 to itself, a fixed symbol, or 1 cycle. Imagine now a more complicated permutation, say of 10 symbols. Since a permutation is a 1, 1 and onto function, in its diagram each symbol will have 1 arrow going out and 1 coming in. And it must break up into disjoint cycles like this. Any permutation can be expressed as a combination of disjoint cycles. We call this the cycle form of the permutation.
Our real interest in permutations stems from the fact that all the permutations of a given set form a group. For instance, all the permutations of a set of 5 symbols forms a group of order 120. The group operation is a natural one. As we've just seen, permutations are functions, and we can multiply functions by the usual composition rule. So let's see now how we can multiply 2 permutations when they're given in cycle form. What about this product, Fg? Here F is a 5 cycle, and the permutation G is comprised of a 3 cycle and a 2 cycle. I want to work out its product. Well, of course, we could reconvert F and G back into their 2-line form and work out the product in the customary way. But as you've probably guessed, I needn't do that. I can work out the product in its cycle form directly, like this. Well, I could start with any symbol. The obvious one to choose is 1. Let's see what happens to the symbol 1 under the product. Now, the first thing to remember is that in a product like this, FG, it's the 1 on the right, the G, that acts first. So let's pursue what happens to 1. Under G, 1 goes to 2. Under F, 2 then goes to 4. So in the product, 1 goes to 4. And 4 is the next element in this particular cycle. We then want to see what happens to 4. Well, under G, 4 is at the end of this 2 cycle, so 4 goes to the 3. Under F, 3 goes to 5, so in the product, 4 goes to 5. Now what happens to 5? Under G, 5 goes to 1. Under F, 1 goes to 3, so in the product, 5 goes to 3. What about 3? Under G, 3 goes to 4. Under F, 4 goes to 1. That's completed the cycle. 3 comes back to 1. And there we've got a 4th cycle. That leaves us now just with the symbol 2. Now, of course, the only thing that can happen to 2 is that it's fixed. Let's just check that. Under G, 2 goes to 5. Under F, 5 goes to 2. So in the product, 2 is fixed. And this particular product, FG, is a 4th cycle and a fixed point. Well, during the program, we'll look at 1 or 2 more calculations of this type.
So any permutation can be written in cycle form. And if you take the group of all permutations on some set, then each permutation can be written in cycle form. And let's do exactly that for S3. That's the group of permutations on 3 symbols. Let's write all those permutations in cycle form. Well, the first permutation to think of will be the identity. That keeps everything fixed. So in cycle form, it'll look like this. Just the 1 cycles. Next, we have the permutations which interchange 2 elements, keeping the 3rd element fixed. And in cycle form, these permutations would look like this. For example, 1 goes to 2, and 2 goes to 1, and 3 is fixed. Now, permutations of this sort, which interchange 2 elements and keep everything else fixed, we call transpositions. In this case, there are just 3 ways we can transpose pairs of elements in S3, and so we get just 3 permutations whose cycle structure looks like this. Finally, we have the 3 cycles which shift everything about. Here's one example. Here, 1 goes to 2, 2 goes to 3, and 3 goes back to 1. And we have just one more case. Here, 1 goes to 2, and the only other possibility is when 1 goes to 3, giving us a 3 cycle like this. If we had any other 3 cycle, for example, 2 goes to 3 goes to 1, it would be just one of these repeated. So here we have the 6 permutations in S3 written out in cycle form. Now, you already know that S3 is isomorphic to the symmetry group of the equilateral triangle. So how do the permutations in cycle form correspond to the symmetries of that triangle? Well, let's have a look by pulling in this model. First of all, there's the identity. Well, as far as the symmetry goes, that is we take the identity symmetry. That also keeps everything fixed. And so obviously, that'll be the symmetry. Next, we have these transpositions. Well, let's take the first one, interchanges 1 and 2 and keeps 3 fixed. And that'd be the same as reflecting in the line through 3. If we reflect in this line, you see, we'll just interchange 1 and 2 and keep 3 fixed. And similarly, the other transpositions correspond to reflections in the same sort of way. Finally, we have the 3 cycles. Well, here, 1 goes to 2, 2 to 3, and 3 to 1. So in our model, that will be 1 goes to 2, goes to 3, back to 1. Obviously, that's just going to correspond to rotating like this. And the other 3 cycle just corresponds to rotation in the other direction. Well, notice the pattern that we've got here. The rotations correspond, in this case, to the 3 cycles. The reflections correspond to these transpositions. And we have the identity in a class by itself. Well, we saw in the first section of this unit that there are 3 conjugacy classes for the symmetry group of the triangle. The conjugacy classes correspond to the rotations, that's one class. The reflections will be a second class, and the identity is in a class by itself. And you notice that we can get conjugacy by looking at the cycle structure, because we get that the 3 cycles will be one conjugacy class, the transpositions another class, and finally the identity. And it turns out that this sort of pattern is not special to this particular case. For the rest of this program, we're going to look at conjugacy, and we'll see that when we're looking at permutation groups, conjugacy and cycle structure are very closely related. Alan.
Well, first of all, let's recap the definition of conjugacy. Two elements F and G are conjugate in a group if and only if there's some element K in the group such that F is equal to the product Kg K inverse. I'll work out an example of a conjugate in the group S5. So I'm going to choose two permutations, G and K, and work out this product Kg K inverse. For G, I'll choose this element. It's a transposition. G interchanges the symbols 1 and 2 and leaves the other symbols 3, 4 and 5 fixed. But before looking at our conjugate, let's just digress for a moment and introduce here what is a standard convention when we're dealing with permutations in cycle form. If there's no ambiguity as to what set of elements we're permuting, it's customary to not write down the fixed points, or one cycles. So I simply say G equals 1, 2, it being understood that the symbols that don't appear, in this case 3, 4 and 5, are fixed. I've applied the same convention to K. Here's K, it's the 3 cycle 1, 2, 5. The two missing symbols, 3 and 4, are therefore fixed. Oh, there's one final problem before we can work out the conjugate Kg K inverse. We want to know what K inverse is. And it turns out that that's easy. There's K inverse. I've got it simply by writing the cycle of K down backwards. Let's just check that that's right. Remember, K is a function. It's a function mapping 1 to 2. Its inverse, therefore, must be a function mapping 2 back to 1. It does. K maps 2 to 5. So its inverse maps 5 back to 2. Finally, K maps 5 to 1, so its inverse maps 1 to 5. So there's a useful thing for you to remember. To find the inverse of a cycle, we simply write the elements of the cycle down in the reverse order. So now we're ready for our conjugate. I want to work out this product, Kg K inverse. Now, so we want to pursue first of all the symbol 1 through this product. Remember, we start on the right. Under K inverse, 1 goes to 5. Under G, 5 is fixed. Then under K, 5 goes to 1. So overall, the symbol 1 is fixed. And by the convention I've just mentioned, I won't bother to write that down. Let's look next at 2. Under K inverse, 2 goes to 1. Under G, 1 goes to 2. And under K, 2 goes to 5. So overall, 2 has gone to 5. It went to 1, then on to 2, and then to 5. So we can write that down. 2 has gone to 5. So to pursue this cycle, we want to know next what happens to 5. Under K inverse, 5 goes to 2. 2 then goes to 1. 1 goes to 2. So 5 has gone back to 2, and that's completed the cycle. We've got a 2 cycle there. The remaining symbols, 3 and 4, are easily dealt with. They don't appear. They're each fixed by K inverse, by G and by K, and hence they're fixed by the product. So by our convention of not writing them down, that's finished our conjugate. This particular conjugate Kg K inverse is the transposition 2, 5. Now there are many other conjugates of this particular transposition 1, 2 that we could work out, for we can form a conjugate for any choice of element K in the group. And this particular group has order 120, so there are a lot of others. But it turns out that any other conjugate of the transposition 1, 2 turns out to be itself a transposition. And what is more, every transposition crops up in this way. The conjugacy class of the transposition 1, 2 is the set of all transpositions. Now, I'm sure that you can't see why that is true from this one example I've done. It's rather a deep statement. So to try and show you why it is, I'd like to go through the same calculation again, but this time do it in a slightly different way. I'm going to work this time with the 2-line form of the permutation, and as I apply each permutation, I'm going to adjust the bottom line of counters. So, first of all, we want to apply K inverse. K inverse was the permutation which takes 5 to 2, 2 to 1, and 1 to 5. Well, to do that, rather than move them, I'm going to pull these labels up. 5 goes to 2, 2 goes to 1, 1 goes to 5, and 3 and 4 are fixed. There, in 2-line form, is the permutation K inverse. Next we want to do G. G interchanges 1 and 2. Well, let's actually do that. We'll interchange 1 and 2, and then we want to apply K. Well now, as K inverse was the function which brought the new labels up, its inverse, K, I'll get by simply taking the labels back down again and getting back to the original labels. But let's check that. K is going to map 1 to 2, 2 to 5 and 5 to 1. Let's check that it really does it. As I take the labels down, 1 goes to 2, 2 goes to 5, 5 goes to 1, and 3 and 4 stay as they are. So I get K simply by pulling the flaps down, restoring the original labels. And this is our overall conjugate. And notice we do get exactly the same result as before. The symbol 1 is fixed, 3 is fixed, and 4 is fixed. We simply interchanged 2 and 5. It's the transposition 2, 5, just as before. But notice, and this is the important thing to notice, the 2 is actually K of 1. And the 5 is K of 2, because remember, K is the function which takes the flaps back down. K of 2 is 5. So this transposition that we've ended up with, 2, 5, is actually the transposition K of 1, K of 2. And it turns out that this is exactly what will happen for any other choice of K. The conjugate K, 1, 2, K inverse will be the transposition K of 1, K of 2. And what's more, if I start with some other transposition, Ij, and form the conjugate K, Ij, K inverse, it will be the transposition K of I, K of j. Well, let's look at this same technique now applied to other permutations. In this next example, I'm going to work out the conjugate of a 3-cycle. I'll work out the conjugate K, 3-cycle 1, 2, 3, K inverse. So first of all, as before, we apply K inverse. And just as before, to do that, I lift up the flaps. I'm not even going to tell you what K is this time. It's not going to matter. I've applied K inverse, and notice that I've left 2 blank. I've only told us at this stage what 1, 2 and 3 now are, because it turns out that that's all I'm going to need. K inverse has just given me a new set of labels. Well, I then want to apply 1, 2, 3. That tells me 1 has got to go to 2, 2 has got to go to 3, 3 has got to go to 1. Well, let's be careful about this just to make sure we don't get it wrong. 1 has got to go to 2, 2 has got to go to 3, and 3 has got to go to 1. Well, now that we've got our check, we can do it. 1 is going to go there, 2 is going to go there, and 3 is going to go there. Well, then we want to do K. I never told us what K is, but we know what K does now. It simply takes these flaps back down again and restores the original labels. And there's our conjugate. What is it? Well, the symbol 1 is fixed, and the symbol 3 is fixed. What are we left with? 4 has gone to 5, 5 has gone to 2, 2 has gone to 4. It's a 3-cycle. It's the 3-cycle 4, 5, 2. But now notice again that 4 is K of 1. Remember, K is the function which takes the flaps down, revealing the original symbols. K of 1 is 4, K of 2 is 5, and K of 3 is 2. So 4, 5, 2 is the 3-cycle K of 1, K of 2, K of 3. So the story's beginning now. We've seen that a transposition is conjugate to all other transpositions. Here we've now seen that a 3-cycle, any conjugate of a 3-cycle, is a 3-cycle. And again, the converse works, namely that in the full symmetric group, every 3-cycle will turn out to be conjugate to this one. To illustrate that, suppose I want to show that 1, 2, 3 is conjugate to 3, 4, 5. What do I have to do? Well, knowing that the conjugate by K is this thing, K of 1, K of 2, K of 3, I've simply got to match these two up. I want to find a permutation K which takes 1 to 3, 2 to 4, and 3 to 5. Well, that's not difficult. Let's see if we can build one. I'm going to build this in its 2-line form. What do I want? I'm simply looking for a K which takes 1 to 3. Well, in 2-line form, 1 has to go to 3. 2 goes to 4. So I want a 4 here. 3 goes to 5. I want the 5 there. Well, it doesn't matter about the last two, I can put them any order, like that. And this permutation K will conjugate 1, 2, 3 to the 3-cycle 3, 4, 5. Well, the story is now building, and using this idea, it isn't much work now to show that any permutation is conjugate to all of the permutations with the same cycle form. For the permutation KG K inverse, if we think of K inverse as introducing new labels and subsequently K taking them off again, we can see that KG K inverse does exactly what G does, but it does it to the symbols as they've first been relabeled. So a permutation and a conjugate of it are similar permutations, that is, they're permutations with the same cycle form. Well, we'll do one more example of this, dealing with slightly more complicated permutations. Here's one in S7. It consists of two 2-cycles and a 3-cycle. Now suppose we want to show that it's conjugate to another permutation of the same form. In other words, we want to find a K such that KG K inverse is equal to this permutation. Think of what that means in terms of the labels we've been using to illustrate K and K inverse. Remember, when we're working out KG K inverse, then at the time of applying G, we apply it to the counters as relabeled by K inverse. So when we finally apply K, by taking the labels off, we want to find that we've really acted on the symbols as they appear in the bottom line. So this picture tells us what K does. The image under K of each number in the top line is the number directly below it. In other words, K is now written in its 2-line form. Any two permutations in Sn with the same cycle structure are conjugate, because we can always find a K by the method illustrated by this example. So, in a whole symmetric group, like S5, we can write down the conjugacy classes simply by knowing the various cycle forms. These are representatives of the conjugacy classes of S5. The 5 1-cycles form the one-element conjugacy class consisting of the identity. But a word of warning. Throughout, we've assumed that we're working with a full symmetric group. If we're looking at a problem involving just any group of permutations, a subgroup of the symmetric group, then it'll turn out that an element is still conjugate only to others with the same cycle structure. But now, all the elements with that given cycle structure might break up into more than one conjugacy class. We'll pursue this point in the text.
So what have we done? Well, we've seen that every permutation can be written in cycle form. And what's more, if two permutations are conjugate, then their cycle structure will be the same. We've also seen that in Sn, the converse is true. That if two permutations have the same cycle structure, they must be conjugate. But why are we making such a fuss about permutation groups? The reason is that every finite group can be modelled by a permutation group. This is what we call Cayley's theorem. Every finite group is isomorphic to a group of permutations. So, if we know everything about Sn and its subgroups, we'll know everything about finite groups.